In the world of robotics, there's this one concept that people often call the holy grail of autonomy. It's the fundamental technology that lets a machine actually understand and navigate our physical world. And it goes by a simple name, SLAM. So let's just start with the most basic question, the one that kicks this whole thing off. How can a robot, whether it's a self-driving car or even just a drone, explore a brand new space, a world that it has no map for, no blueprint, nothing? This is without a doubt one of the biggest puzzles in all of robotics. And that question immediately leads you to this fundamental paradox. It's a total chicken and egg situation. Think about it. To build a map, you have to know where you are on that map. But to figure out where you are, well, you need a map to begin with. So how on earth do you solve for both of those things at the exact same time? Okay, so let's dig into that a little bit more. This paradox, it has a name. And figuring out how to solve it is the absolute key to unlocking true freedom for robots. It's called SLAM, and that stands for Simultaneous Localization and Mapping. And honestly, it does exactly what it says on the tin. It's the process of building a map of some unknown place while at the very same time tracking your own position inside that very map you're creating. This is literally how a robot goes from being completely blind to having a real sense of its surroundings. Now, I know that can sound a little abstract, so let's try a simple analogy to make this whole complex idea feel a lot more intuitive. I think this will make it click. Okay, picture this. You wake up in a house you've never been in before, and it's pitch black. The only thing you have is a small flashlight. As you start to walk, that little beam of light lands on a sofa, so you make a mental note. Okay, sofa's right there. You take a few more steps, and now you see a doorway. You see what you're doing? You are building a map of the house in your head while also keeping track of where you are in relation to the things you're finding. In a nutshell, that's what SLAM is. It's just a robot doing what we do naturally. So that makes sense for us. But how do robots actually pull this off? Let's break down the step-by-step workflow they use to constantly solve this paradox. The whole thing works as a loop that just runs over and over and over. First, the robot's sensors, its eyes, like cameras or lasers, are constantly grabbing data about the world around it. Second, it sifts through that data to find unique features, like the corner of a table or a specific pattern on the wallpaper. Third, it estimates how it's moved, and it adds those new landmarks to its growing map. And fourth, and this is the part that is absolutely critical, it does something called loop closure, which, as we're about to see, is where the real magic happens. And I really want to emphasize, this isn't a one-time thing. The robot is constantly cycling through these steps. It's a nonstop loop of sensing, mapping, and self-correcting that just gets more and more accurate with every passing second. And this brings us back to that crucial last step, loop closure. This is basically the robot's big aha moment. See, as it moves, tiny little errors in its sensors start to add up, and it causes the map to kind of drift out of shape. But when the robot gets back to a place it's been before, it recognizes it. It realizes, hey, I've seen this spot. And with that recognition, it snaps the entire map back into alignment, correcting all those little errors that have built up. This is what makes the map reliable over long distances. So how does a robot actually see all this stuff? Well, there are really two main ways. On one hand, you've got LiDAR SLAM. This uses lasers to build these incredibly precise 3D point cloud maps. We're talking millimeter-level accuracy, and it even works in total darkness. The catch? It's expensive. The other approach is visual SLAM, or VSLAM, which just uses normal cameras. It's way cheaper, and it can provide really rich information about what objects actually are, but it needs light and it's a little less precise. The choice between them really just depends on the job. And believe me, those jobs are everywhere. This isn't just some theory stuck in a research lab. This technology is already in our homes, on our streets, and it's even pushing the boundaries of space exploration. The most common example is probably your robot vacuum cleaner. It's not just bouncing around randomly. It's using SLAM to build a little map of your living room, so it knows where it's already cleaned, where it still needs to go, and how to do it efficiently without getting lost under your couch. But now let's raise the stakes. Self-driving cars and autonomous drones absolutely depend on SLAM. Now you might be thinking, what about GPS? Well, GPS is great, but it can be off by several meters, and it totally fails in tunnels or between tall buildings. For a car moving at high speed, a few meters is the difference between being safely in your lane and being in a head-on collision. SLAM is what provides that crucial centimeter-level accuracy that makes safe autonomy possible. And its reach goes even further than that. In medicine, SLM helps guide tiny surgical tools inside the human body, a place where GPS obviously won't work and where millimeter-perfect precision is a matter of life and death. Or think about huge warehouses, where whole fleets of robots navigate and move goods without needing any tracks painted on the floor. It completely untethers them, making the whole logistics system incredibly flexible and efficient. So it's pretty clear that SLAM has already transformed our world. But what's really exciting is that right now, it's getting a massive upgrade, a supercharge, really, thanks to modern artificial intelligence. Let's take a look at what's coming next. AI is boosting SLAM in a few key ways. First is something called semantic SLAM. This gives robots actual understanding. They don't just see an obstacle, they know this is a chair or that is a person. Then AI helps robots deal with messy, dynamic places by learning to ignore moving things like people walking by, so they don't get incorrectly burned into the permanent map. And finally, there are these mind-blowing techniques like NeRFs, which allow a robot to create stunning, photorealistic 3D models of a space from just a handful of pictures. Which really brings us back to where we started. We asked how a robot can explore an unknown world. The answer is SLAM. It gives machines the ability to see, to map, and to understand their own surroundings. So the real question now is, if SLAM has given robots eyes, what new worlds are they going to show us next?